Yeah. Interesting. Not the whole thing. All right, guys, let's get started. Last time we talked about the Gram-Schmidt process for orthogonalization, and we didn't get to the QR factorization, so we'll do a little bit of quick overview of that today, the whole QR factorization idea. But of course, anything new that we learn will be based on some of the stuff that we should already have known or have learned. And so the Gram-Schmidt process allows us to create from a set of any random set of linearly independent vectors, or a basis they call it, to create an orthogonal, not just orthogonal, but orthonormal set. So we're adjusting our basis vectors to make it look like they're all mutually orthogonal and they all have unit length. So the mutually orthogonal part is based on the idea of the projection, orthogonal projections. And so well, the last step is to normalize the set. So our orthonormal set of bases will start with the first vector, and then from the first vector, we create another vector that's going to be orthogonal to the first vector by doing the orthogonal projection. Now, orthogonal projection onto vector v1 is just this part, but remember, when you subtract your new vector with the orthogonal projection, that's going to be perpendicular. And so in this picture, we have that perpendicular, we have those two vectors that we're going to make perpendicular. And then, so now this new vector is v2, it's orthogonal to v1. Now from there, we're going to redo the same thing by projecting v3, the third vector in your set, onto the vector or the plane, the space that spans the first two vectors, v1 and v2. And this thing that's highlighted right now is the actual orthogonal projection. And then when we subtract it, then we actually get the orthogonal vector. So that's how the Gram-Schmidt process works. And then after you do that, you have a set of orthogonal bases that span the same space. And then the last step is to normalize all of them so that you have an orthonormal set. And that's kind of like what you guys did in the activity. And so let's assume that you guys know how to do that already and move on. April. So now we're going to talk about the QR factorization because we ran out of time. QR factorization is our second way to factor a matrix. So kind of like the LU factorization, we have a QR factorization. Of course, we didn't go over it until now because we needed to know how to orthogonalize a set of basis vectors so that we can use that, and that's what Q vector or Q matrix is going to be. So if we start off with an m by n matrix, notice it doesn't have to be a square matrix, with linearly independent columns so that we can use the columns to span the space that we're spanning. Then A can be factored as A equals Q times R. Now Q is an orthogonal matrix. Orthogonal matrix, remember, has column vectors that are orthogonal and normal. So that's orthogonal. And R turns out to be a triangular matrix. Not only that, but it also has positive entries in its diagonal. So that has a lot of values in doing a bunch of computations. So it would be good for us to know that. Since Q is an orthonormal, has orthonormal columns, then Q T times the transpose of Q times Q is going to be equal to the identity. I think we did that as a proof for one of the things that we got from the homework set. And then it turns out that if you have this QR factorization, think about multiplying by the inverse on both sides, on the left side of both sides. And the inverse, remember, is the transpose. So we have QT times A is equal to R. And that is actually how we're going to find R. So we're going to find the Q matrix by creating an orthonormal set of basis vectors for the column vectors in your matrix. And then we're going to find R by multiplying A times the inverse of Q, or the transpose of Q, on the left side. And so that's how we're going to get your R vector. So here are the steps. You find a set of orthonormal vectors for the columns of A, and then create a Q matrix, and then find QT times A to get your R. Okay? So let's do an example. Oh, yeah, let's do an example. So here's an example. Here's a matrix, a 4 by 2 matrix, which is clearly not a square matrix. Oops. Sorry. So let's go through. This is kind of simple because there's only 2 vectors. There's only 2 columns involved, but I think it's enough of an illustration to figure out what happens here. So we're going to let our vectors x1 and x2 be the columns of the matrix A. Now let's just double check. If you take the dot product of these 2 vectors, is it going to equal to 0? Or let me rephrase the question. Are these 2 vectors already orthogonal? So you can check by dotting. So it's not orthogonal, so we have to orthogonalize it. And in this case, since there's only 2 vectors, this is going to be just a one-step Gram-Schmidt process. So we're going to let V1, I don't know if this is necessary, but we're going to let V1 equal to that first vector. And now V2, according to the Gram-Schmidt process, is going to be equal to V1 minus, and then the dot product of your vector V2 with, your vector V1. Wait a minute. X2. Yeah, there you go. It's X2 minus. Thank you. All right. So this is X2, right? So we have -1, 4, -1, 4, minus some constant that we're going to figure out, and then V1 is 1, 1, 1, 1. So let's figure out that constant, that scalar, I mean. So it's X2 dotted with V1. That's really X1 and X2 dotted together, right? What do we get? 6 for the top and 4 for the bottom. 16, 16, 17, 18, 36. Yep. Nope. What? Oh, 4. Is that right? Not 2? No, it's 4. All right, so 6 over 4, what is that known as? That's 3/2, right? So let's finish the calculation. Minus 1 minus 3 halves, that's minus 5 halves. 4 minus 3 halves is 5 halves? No. Is it 5 halves? Positive. And then these things look like it repeats. Okay. So now we have to find the magnitude so we can normalize it. So we have these v vectors that are orthogonal to each other. Let's create u vectors now so that it's normalized. So this is 2, right? The magnitude. It's 4 when it's squared, or when it's without the square root, right? And you need to take the square root of it, right? And then I think since these are all the same, it would be the same, right? 4. And then factor out the 5 halves, and then it'll be 5 halves. It's what? 1 over 5, 5 halves. 1 over 5, the 5s would cancel. Okay. So those are our 2 vectors. So with that, we're done with Q. So it's 1/2, 1/2, 1/2, 1/2, and minus a half, positive a half, minus a half, positive a half. That's our Q vector. Okay. Questions? So now to find our R vector, we would multiply that with would multiply the transpose of this with A. So R is going to be Q transpose times A. So Q transpose is this thing written sideways. I mean, transpose minus a half, positive a half, minus a half, positive a half, and then multiply that with A. 1, 1, 1, 1, negative 1, 4, negative 1, 4. And we should get, according to them, we should get an upper triangular matrix with positive entries in the diagonal. And this is a 2 by 4 multiplied by a 4 by 2. So what's our matrix going to be? Should be a 2 by 2 matrix, right? So this is just 1/2 being multiplied all with 1s. That's 2, right? And 1/2 being multiplied. So this is a negative a half, 2, negative a half, 2, positive 3. And then now we have negative 1, negative 1/2, positive 1/2, negative 1/2, positive 1/2, and then positive, positive. So that's 1/2 plus 2 plus 1/2 plus 2, or 5, 5. This is your R. That's it. And if you multiply Q times R, we should get your original matrix A back. Okay. So now we can factor another way. So our first way to factor was to factor so that we have an LU decomposition, and then now we have another way to factor QR. Yeah. Wait, say it again? Oh. Yeah. Will help us get that. Because it's, yeah, because it's an upper triangular, it's nice and easy to deal with. All right. So that's the QR factorization, right? Okay, so we're going to move on. We will use a little bit of the QR factorization when we go on to our either this section or the next section. We're going to be talking about the least squares problem. Now for this, I want to try to see if I can remember how far back. We are moving on to 6.5, yes. Can't seem to find it. Is it here? No, that's the Gram-Schmidt. That would be the time before. Orthogonal sets. Orthogonal projection. We went over a theorem called the best approximation or least squares or something like that. Do you remember what day that was? Oh, well. We'll do a recall. So I'm not quite sure what section this is from, but this is from one or two sections ago. The best approximation theorem says that if you have a subspace and then if you have a y is some vector in the subspace, not in the subspace, not necessarily in the subspace, but just y in some vector space. Then y hat is the orthogonal projection of y onto w, and then w is the closest point, or I mean y hat is the closest point in w that best approximates the y vector. That might sound a little confusing, but because it is, but let's see if we can put this in a simple two-dimensional perspective, 2 and 3-dimensional perspective. Let's just, for the sake of viewing this, let's let W be a plane subspace in R3. Okay, so it's spanned by a couple of vectors in R3. So let's say we have a couple of vectors in R3, and then W is going to be the plane spanned by these two vectors. And then we have a vector y in R3. I'm going to deal with vectors the whole time, so I'm not going to draw arrows because of the hat thing will kind of might make it look confusing. And so what this is saying is that y hat is a vector that's on W, that's actually on the plane, that is the best approximation to y. Best approximation in the sense that if I'm just restricted to staying within y, and I want to figure out, I mean, if I'm restricted to just a vector in W, and I want to find a good representation for y, the orthogonal projection of y onto W is going to be this vector over here, which is going to be the best approximation to y that is not necessarily on the plane. If it's on the plane, then y and y hat are equal to each other, and then you're done. That's it. It's not just an approximation, but it actually is the same vector. But if y is not on the plane, and I can only represent vectors that are on the plane, then I would look for the best approximation, and the best approximation will end up being that orthogonal projection. Does that make sense? So that's what y is. A y hat, thank you. That's what y hat is, and that's the relationship. And so what they're saying here is that if you have any other vectors v in W, then it's always going to be bigger than. All right. That's the best approximation theorem. So now we're going to move to the least squares problem. And the least squares problem tells us that if you're trying to solve for an equation, ax is equal to b, which is something that we've been doing almost more than half the semester, sometimes you might not get a solution. So if you don't get a solution, what's the closest thing you can get? So we're going to move to this idea of approximation. So it turns out that the general least squares problem is finding an x vector so that the difference between ax and b, the magnitude of the difference or the length of the difference, is going to be as small as possible. It's called least squares because the magnitude, remember the computation for the magnitude, it's a square root of a whole bunch of things squared that you're adding together. So it's the sum of those squares is what they're referring to as a least squares problem. So the least squares problem is this problem that we want to approximate. We don't get an exact solution, but let's find an approximation as best we can. So the approximation as best we can is trying to solve for this least squares problem, and the least squares solution is going to be should be an Rm. It should be a vector in Rm All right. So the solution is that vector that gives you the smallest difference between your b vector and a vector that's in ax. the span of AX. Turns out that it's going to be in the span of the column vectors of A. So the question is, what is A, or how does A play into this, the matrix A? Yeah. So which one's RM? Wait. Is in RM? This is RM. Ah. Thanks, Brian. Should be RN also. So I changed the wrong one. Wait, no. Really? So A, 1, 2, 3, 1, 2, 4. Yeah, yeah. Okay, that's right. Thanks. All right. So what does all this mean? This means that the solution that we're looking for is not necessarily the projection, but the x vector that leads to that projection. So this is a little trickier even, because it brings us out of this picture, and then it means that we're dealing with something else before dealing with this picture. What? I don't know. Yeah. So the application that we're going to look at in detail is like the line of best fit. If you have random points, and for those people who have taken statistics, this should look familiar. So this is a topic in statistics called linear regression. If you have a bunch of lines and you want to make it fit into, if you have a bunch of points and you want to make it fit into a line, not every single point is going to be on that line. If every single point were on that line, then this process will have an exact solution. But we can still try to mimic those points with a line, even though some of them will have some distances away from that line. And so that's the close. We want the closest. We want the one that would give us the least error when we draw that line. And we'll do that by finding the distances here. And the distance here end up to be the square root of the squares, which is why it's called the least squares line. Okay. All right. So what was I trying to say? I was trying to say that we're going to relate this into spaces, not only spaces, but we're going to relate it to the column spaces, and then we're going to move to an example. So here's our scenario. So AX is actually a column space. It's actually in the column space. So if you look at this idea of multiplying the matrix A times a vector X, you're essentially getting these columns, and then you're multiplying it with x1, x2, x3, and these are just like the weights of all these column vectors. right? So AX is actually in the column space, and the column space, as we know, is a subspace of um, R n, R n, the number of columns. No, Rm, the number of rows. We're looking for X that makes AX as close in column A as possible. And then if B is in column A, then the system, this is where you actually get a solution. So looking at this drawing, if Y is actually on the plane, then that's going to be the solution. But if it's not on the plane, then we use the best approximation theorem, which states that there's going to be some X values that would make that happen. And then the closest value we get is that column is projecting your vector onto the plane. All right, let's try to see if we can illustrate this with an example. And I made the example. I copied this is problem number 1 from the homework set or from the exercise set, and it's a 3x2 matrix. So we can imagine that n is 3. So we're talking about a vector space in R3. And then we have 2 columns that are linearly independent. I hope they're linearly independent. And then they would span, the column space would span a 2-dimensional plane. M by n. Yeah. Well, let's get this straightened out. So A is 3 by 2, m by n. So m is equal to 3 and n is equal to 2. Okay. Yes, you're right. So we're looking at a 3-dimensional space because the column space is in 3 dimensions. Now, but it's only a 2-dimensional vector in 3 dimensions. So a column, so let's just say that columns are linearly independent. So because the columns are linearly independent, we don't have to go do that row reducing business and figure out the rank and stuff. The rank's going to be equal to 2 because that's the number of linearly independent columns we have. So column space is going to be the span of these 2 vectors, -1, 2, -1, and 2, -3, 3. So we can imagine our W, which is in this case the column space of A, being spanned by these 2 vectors. Let's call this V1 and V2. Now we have a vector B. Let's see where B is. The question is, can we write AX equals B? So the question is, can we write 1, 2, 2, -3, -1, 3, 4, 1, 2? Can we do a row reduce here real quick? MATLAB? Sure. Look, MATLAB's already open. So let's see. I have a vector v1 is equal to -1, 2, and -1, and a vector v2, which is equal to 2, -3, 3. These are column vectors. And so your matrix A is going to be the combination of v1 and v2. Okay, that turned out right. And so B is going to be 4, 1, 2. Oops. So if we want to augment this, and row reduce, you see it looks like the identity, right? So the thing is that if you look at this last row and we're solving for this, we're solving for like x and y that would make this, or x1, x2 that would make this 0. We have an inconsistent system. What? Sure. So what we have here is a B that's not in the column space. We don't get a solution, so that means B is not in the column space of. By the way, let's go back to the original problem, and since we're looking at A being an m by n, a 3 by 2 matrix, AX equals B. So B clearly is 3 by 1, and A was a 3 by 2. So what do you think X is? So X is a 2 by 1 matrix, right? So this is when I was trying to explain earlier, X actually comes from another space. So the X vector is some vector in R2, and that vector in R2 transforms. So this vector in R2 is transformed by A onto a vector in R3. So I wanted to point that out because the solution to our least squares problem comes from this two-dimensional vector. So this is the solution that we're looking for. And so you should know what the dimensions are of the solutions you're looking for. Okay, in this case, it's a two-dimensional solution. All right, so we found out that the system is inconsistent. So obviously we're going to use this information to try to solve for this solve for the system. And what we need, I'll do this in blue, is we need this vector that we're going to call B hat that's going to be in the column space of A. That's going to be the best approximation to B. Okay? So what are we looking for? We're looking for an orthogonal projection. We're looking to project this onto this plane. So orthogonal projection, solve for B hat, which is going to be the projection of B onto the column space of A. Which means we have to take our vectors in the column space, right? And then do the orthogonal projection. So the orthogonal projection here, what's the orthogonal projection? Yeah, so we need to do it for each column. So we got V1 and V2. I don't want to call it U yet, but W. Let's call it W. So what? We have a vector in R3, B. X is in R2, but let's just put that aside for now. That's what we're going to solve for. No, that's not quite the reason. So this vector X is something that I kind of introduced that I should have probably brought up earlier, but when we solve for this, we're going to talk about, after we go through the process of finding out B hat, we're going to see what X actually means. Okay, that the two-dimensional vector. But so far, what we have is a vector B in R3 and two other vectors, V1 and V2, that span a plane in R3. So they're all in the same space. And then I want to find a projection, orthogonal projection from B onto the plane. And that's called B hat. And then what I'm going to do is I'm going to relate B hat with this X on this other plane, other space. Matt first. No, it's not W. Thank you. This is not W. This is some other space that exists, and there is AX. AX. AX is a vector in R3. AX is a vector in R3, but X, well, it depends on what A is equal to, but A transforms X to that vector in R3, but it comes from somewhere. We don't care where it's coming from. We're trying to find out what it is. But yeah, we're trying to find out what that value is. Matt, does that make sense? Because those are, when it comes down to the actual problem, those are the solutions. The solutions are these X. Which is an estimate, right? That's not quite the reason. Yeah. So the A maps a vector onto another vector space. So we've been looking at this other vector space, but we have to remember we're the original thing that we're solving for was in this other space that A had already mapped. And so that space is the space that we're kind of not caring about until the very end when we figure out what's happening in this new space that we're dealing with. How X is translated, right? No, A translates X into the new space. Bob? So W is, in this case, it's the column space of A. W is a subspace of some n-dimensional space. In this case, W is column space of A. which in this case, again, happens to be a two-dimensional plane in R3. We're solving for B hat, and then we're going to backtrack and solve for X hat. Yeah, okay. So hold on to your thoughts and questions because we're going to go for a ride and hope we don't crash. Because maybe when we get to the end part of this and then we backtrack and solve for X naught, it might be a little clearer, hopefully. All right. Now, what was W? Just a space, yeah. All right. So I don't want to use W because it's the column space. So I have V1 minus 1, 2, minus 1. And then I want an orthogonal projection, V2. So I want to use a different symbol instead of V2. Well, let me write it down first. 2 minus 3, 3. So I want to orthogonalize this using the Gram-Schmidt process. Right, so that's why I don't want to use V1 and V2. So let's call V1 prime. It's not a derivative. It's just another letter. V2 prime is going to be equal to V2 minus V2 dotted with V1 divided by V1 dotted with V1 times V1. So that's the stuff that we just did previous, right? So V2 is 2 minus 3, 3 minus something times V1 is minus 1, 2 minus 1. So I need this dot product between these two. That's negative 2, negative 6, negative 8, negative 3. That's negative 9 is what I got. Is that correct? Hmm? This is negative 11? Where did I get negative 9 from? And then V1 dot V1, 4, 6. So what do we have here? This is plus, plus, minus. So 11 over 6 for the first one. Negative 11 over 6. 1/6. Can you just tell me the answer? I think that's what I think. No. Oh. Yeah, I was doing the subtraction already. Well, here, why don't we do it this way? Yeah, we should probably do that because clearly I'm not accomplishing what I want here. So plus, plus, negative, so negative 11 over 6. Plus, plus, it's positive 22 over 6, 11 over 3. And then plus, plus, negative 11 over 6 again. 1/6. 2/3 and what? Whew, man. All right, so this vector now, V2 prime is perpendicular, it's orthogonal to V1 prime. So that's good. Now we can project anyways, you know that so this vector v1 looks like this. This vector v2 looks like this. So v1 is equal to v1 prime. Now v2 prime is going to be perpendicular. v2 prime is the new vector that we just found that's perpendicular to v1 prime, or v1. You need to normalize them if you're going to try to create an orthonormal basis, but in this case, we don't care about this being unit length. Actually, we don't even, size doesn't matter in this case. So we can factor out, just for the sake of dealing with nice numbers, we can factor out maybe a 1/6. Yeah, it's is that okay? The other thing is that I tried without making this orthogonal, and it didn't work out. Because the Gram-Schmidt process tells you to make things orthogonal before, because we still have a b vector that we want to project, and that's what we really want. Um, do I need to take out a 1/3 or 1/6? Okay. All right. So this vector is perpendicular to v1, but for the sake of doing the next step in the Gram-Schmidt process, the size of this vector doesn't really matter. So if I make this into some scalar times this vector, this 1, 4, 7 is still going to be orthogonal to the original vector v1. And so with that, I'm dealing with nice whole numbers instead of fractions. All right. Oh, we're out of space already. So now I have this setup over here, which spans a plane. I have a third vector b that's probably not on this plane. Well, we know that it's not on that plane. And I want to project this. So the projection of b onto column A, that's the b hat that we're looking for, is going to be b dot v2 prime divided by v2 prime dot v2 prime times v2 prime. How come I don't have that b in front, b minus this? You're not looking for the orthogonal project. You're not looking for that vector that's orthogonal to the plane. You're looking for just the projection part of it. Correct. All right. Well, I'm just going to go ahead and open this up again. So let's see if we did that correctly. We got well, can we do this? This is B, 4, 1, 2, dotted with V1. So 4, 1, 2, that's -4 plus 2, -2 plus 2 minus 2, -4. And then V1 dotted V1. Oh, wait, I did this. Still 6. I did it backwards, sorry. I did V1 first. So V2 prime is this one. Remember that 1, 6? We can keep the 1, 6 there if we want. Sorry. All right, let's dot B and V2 prime. That's 4 plus 4 is 8 plus 14, 26, 24. 8 plus 14 is 22, 22, 24, 26, 22. All right, this dotted with itself is 1, 16, that's 17, 17 plus 49. Maybe I should do it the other way. 49 plus 1 is 50, 50 plus 16, 66. Yeah. Say it again. Yes. 20 what? That's B hat. So I'm going to have to go. I should have done this on a whole new page. Can I? Oh, wait, all the stuff is not here. That didn't work. All right, what do we have so far? No? All right, what is it? Oh, just 103? Okay, whew, man. Let's collect our thoughts so far. So B hat equals 103. So AX equals B, remember, was our original problem. Yeah. So we have B hat minus AX is the smallest distance that we're looking for between B and B hat, right? This is like B hat minus B. We want this to be as small as possible. So what we want to do is we're going to solve AX equals B hat. Right. B is a projection. So B hat is what's on the plane. So this is V1 and V2. This is B, and this is B hat right here. Yeah, so this is what we have so far, right? But the solution, remember, the solution is X. So we still need to find X. So remember that this is where this strange X, this X vector, A takes that X vector onto this space. So we still need to solve for X here. So yeah. So -1. So -1. What is it? 2, -1, and then or x1, x2. So what we're solving for here is the vector x hat that takes this x. Yes, that's what we're going to want to eventually get. This is, well, yes, we can call it x hat, but we're initially trying to solve for x, and we found that it was inconsistent. So we want to get there as close as we can get. And hex x hat is going to be the solution that we're looking for. So now we're solving for this, which should work because 1, 0, -3 is in the span. That was at B. That was in the column space. So minus 1, 2, -1, 2, -3, 3, 1, 0, 3. If we row reduce this, we should get a solution. And so let's see what we get. We got the vectors A, or V1 and V2, right? V1 and V2 are still the same, so we just need a new vector for V3. So V1, let's say temp again, is equal to V1, oh, let's just call it A, I think. And then, how am I going to put this? Say B hat. B hat is equal to 1, 1, 0, 3. And so RREF, the vector. Yeah, I didn't do temp anymore. B hat. So this is the matrix that we have here, right? And then I did the RREF of that, and then I get 1, 0, 3, 0, 1, 2, 0, 0, 0. So this has the zeros in the bottom, and that means x2 is equal to 2, and x1 is equal to 3. And those are your solutions. Okay? Boy, that was rough. The idea of the process that we did, I think, is the most important part, and I don't know if it was worth it, but this is not how we would normally solve for this. Yes, there is. But I went through that process to show you the orthogonal projections that are happening and how it relates back to the previous sections that we've been working on. Yeah. Well, we can say x hat is this, or actually even better, x hat is equal to 3, 2, yeah. Okay. By A. Well, no, well, this vector here is a vector so that if it gets applied to A, it becomes B hat. And that is the best approximation to B. So this is a solution. Since we don't have a solution for A going directly to B, we have A going to B hat, and that's the closest we can get. Yeah. No, because if it's inconsistent, then there's no actual solution, and so everything else is an approximation. Yeah. No, x hat comes from a different space that goes into the B hat. The matrix takes it to B hat. Yeah, it's the components. The idea that it's the components are more important than it being an actual vector. All right, let's actually see how we should solve for this in 2 minutes. All right. So the idea is that B minus B hat, remember, it's that perpendicular vector, and A of t is a transpose of t, which means now you're kind of dotting the column vectors. You're dotting the vectors with each of these things. And when you do that, that should equal to 0. So if that's equal to 0, then we can distribute the transpose and then bring one of the terms to the other side, and we get this relationship right here. Okay, so A transpose times B is equal to A transpose times A times the x hat that we're looking for. So sometimes this matrix equation has a bunch of equations in it, built in, and that system of equations is called normal equations for AX is equal to B if this AX is equal to B is inconsistent. So now the theorem tells us that we can actually create this to solve for this system, the least squares problem. So this is going to take 2 minutes, but we're out of time. Should I do it? Okay. So we have A right? And A transpose that we want to multiply. So we have A transpose times A is a 2 by 2 vector. Notice it's symmetry. So 6 minus 11 minus 11, 22. So A transpose times A is 6 minus 11 minus 11, 22. The x, y is unknown right now. And then we want A transpose times T, or times B. So A transpose times B, A transpose times B is minus 411. So now you're really solving for this problem, which is just RREF. So RREF, we got 6 minus 11 minus 4 and minus 11, 22, 11. And we get the same solutions that we got last time. What was it, 3 first? Okay. Got 2 minutes? 2 minutes. Thanks for sticking around. Next time we'll apply this to some statistics.